Okay, let's start with our hearing and equilibrium. So dealing with those two senses. So looking at our sound waves and figuring out how balanced we are. So in order to detect a sound, our hearing is a response to vibrating air molecules. So that's how we get our sensation of sound, how sound can travel across a distance. Equilibrium is the sense of motion, body orientation, and balance. So knowing essentially where we are in space. So both of those both of those senses are part of a maze of fluid-filled passages, so up here in this top corner, that have little hairs in them that move when the fluid moves, and so therefore we're able to detect either our vibrating air molecules or the movement of our head and possibly our body, since our head is still attached. So that motion, because of the hairs moving in the fluid, that motion is converted into action potential so our brain can understand what's going on. So let's focus on sound. So again, these vibrating air molecules, depending on how fast they are moving, so how many waves per second, it's going to determine the pitch of the sound. So whether something is a high-pitched sound, like a squeaky little bird, or something that is a lower pitched sound like a roaring lion, is going to be determined by how many waves per second. So a high frequency or high pitched sound is going to be many waves per second. A low frequency sound or low pitched sound is going to be few waves per second. Higher frequency also going to have higher energy. Low frequency is going to also have lower energy. Now for human hearing, our range is 20 to 20,000 hertz. For example, dog whistles is above that 20,000. That's why we actually can't hear it, but dogs can. Speech is about 1,500 to 5,000 hertz, depending on who is talking. Most of your hearing loss is going from 250 to a little over 2,000, which does cross in this range, and that's why sometimes Grandpa can't hear Grandma talking. Wait, it's the opposite situation. Lower waves per second is the lower pitch, so losing the lower pitch end of the talking range. So he should hear Grandma talking as long as she keeps a higher pitched voice. But if her voice is a little bit lower, yeah, he can hear her. It's okay. Now, with our sound waves, not only do we have to worry about deal with the how many waves per second, we also have to deal with how tall these waves are. So if we have a sound that has really tall waves, which is a really loud sound, if it is over 90 decibels, so that is one of our measurements of sound, you actually can cause damage. So our loudness, that is determined by the height of these sound waves. And again, that is measured in decibels. So 0 is the softest that we can hear, and then it goes all the way up to about 140 decibels. That's where we have instant hearing damage. So looking at these two different sound waves, the taller one is a louder sound, so like my voice when I talk. The softer one is a shorter wave, so basically like a librarian when they talk. So we have different sounds on our little scale here. Up here where you have the lawnmowers, that's why sometimes you'll have people who are out mowing their lawn and they have the headphones on to protect their ears from damage. Depending on how loud you play your headphones, you could be just causing damage even though you're rocking out to your favorite song. Turn that sucker down, please. Same thing with people who are working on the tarmac at a airport, while they always have those headphones on, because when a jet engine takes off, that sound is 140 decibels because you are moving a ton of air to get that heavy plane off the ground, and so that's going to cause a loud sound, and therefore if they take those headphones off that are protecting their ears, yeah, they're going to cause some hearing damage. So how do we detect the sound? So let's look at our inner ear structures. There's some labeling of this. I don't know where I put this though. There is some labeling of this. I think, and I might be on the study guide, that the labeling is just these portions in red, which makes sense to what I would have done. So I'm actually going to make sure that is obvious on this slide when I actually teach this. Okay, let's go on the outside and go or towards the inside. So our little big ear flappy thing on the outside, that is called our auricle. So this helps to funnel the sound toward the ear. As we go down our auditory canal, or just our ear canal, so we're going to pass through this canal, this open space, our external acoustic meatus, and getting to our tympanic membrane, which is also called our eardrum. So when our vibrating airwaves hit that eardrum, it's going to cause that eardrum to vibrate. The vibrations are then passed along our 3 inner ear bones called our ossicles, and that information is then sent to our cochlea, which is this portion that kind of looks like a snail shell. We have our detection of sound, and then it's sent on our cochlear nerve to join with this other nerve that I'll talk about in a second to form our vestibulocochlear nerve. The other portion are the semicircular ducts, so we'll talk about them later, dealing with our equilibrium. That information of head movement is sent on the vestibular nerve, joining with our cochlear nerve to form our vestibulocochlear nerve, which is our cranial nerve number 8. So there are ways to protect our hearing, and you've probably had this happen and probably didn't realize it happened. So with our ossicles, our inner ear bone, they actually have muscles attached to them that can help move them out the way so that you have a decrease in the transfer of energy to the inner ear, and so therefore less of the sound wave movement is sent to that inner ear and less likely to damage the structures there. Because when you have damage to your auditory pathway, your brain makes up stuff because it doesn't have a way to shut off you always hearing stuff, and so it's just going to make up stuff. As in that ringing noise in your ears that you occasionally get. Now, that's partially somewhat normal. But for some people, that noise is all the time because of the damage that they have. And so that's just the brain making up stuff, as in, I should be hearing something in this frequency. But because there's damage in that frequency, it just makes up that ringing noise. I literally spent 4 years researching that, by the way. So yeah, I know all about that. Okay, so another way is the tympanic reflex. So we're talking about our tympanic membrane, which is our eardrum. So there is a little muscle called the tensor tympani that can pull our tympanic membrane, so our eardrum, inward, tensing it up, make sure that that eardrum doesn't flap as much, and that therefore helping to reduce the motion that is being sent to the inner ear structures, and therefore less sound, possibility of sound damage. So sometimes, of course, you've been this where you hear a loud sound and then for some reason it sounds a little muffled. It's because you're having this hearing protection happen just so you can protect your ears. So how do we actually detect sound? So if I took my cochlear, my snail shell shape, and I unroll it out straightward, then I have what kind of would look like this structure. So the vibrations on our eardrum passing through our inner ear bones, those vibrations are sent along the fluid in the green space, and it's going to cause movement of this little red section called the basilar membrane. So with our basilar membrane, one part is attached here. The other part is actually free flowing, and it also has a difference in shape, and that also helps with the sound detection. So if you have a low frequency sound, so this is few waves per second, you're going to have more of a response at this distal end. So this is how our brain is able to map out the sounds and know how many per second is because of where it's getting stimulated. Medium in the middle portion, and then our higher frequency sound here at that proximal end, which is more likely of why if you do have a hearing damage for like loud noises or whatever, most likely that tinnitus, that ringing in your ears, is most likely going to be a high pitched sound. So how do we actually code for our hearing? So we have loudness is determined by how much it's going to move. So remembering our louder sounds are going to have taller sound waves, and so therefore you're going to cause that basilar membrane, whichever section the pitch of that sound is going to move a whole lot more. So because of all that moving, you're going to have a higher frequency of action potential. So your brain's like, ooh, that's a loud sound. Okay. With pitch, so it's determined by what part of the basilar membrane vibrates. So just depending on the loudness is going to flap it more, but which section is going to determine the pitch. So something near the proximal end is going to be higher pitch. Something near the distal end is going to be lower pitch. So kind of like the basilar membrane kind of acts like a xylophone. So whichever end is being rung, that is going to be the pitch or the sound, the pitch or the highness or lowness of the sound. So let's look inside our cochlear. So we've taken a pie slice out of it so we can see inside. Here is one of those chambers. Green areas coated like we had last time. This is where the vibrations are going to cause vibrations in the fluid in that area. We cause movement of the basilar membrane below it. So this basilar membrane, when it moves, it's going to cause the hair cells on top of that basilar membrane to also move. Now with these hair cells, the tips of them are embedded in what's called the tectoral membrane. So that stays in place. So when our basilar membrane moves, causing our hair cells to move, that's going to yank on these hairs that are embedded in this tectoral membrane. So when that happens, you have a pulling. So our gated channel is a mechanically gated channel. So you actually have to pull on them to actually open it. So when that happens, instead of sodium coming into the cell, is actually potassium coming into the cell. And then you have your signal of action potentials that are going to send it to the brain. So wherever you are in the basilar membrane is going to determine the pitch, what is sent to the brain, how fast this is moving, how many action potentials are being sent from that specific section is going to determine the loudness of the sound. So here are our hair, the ends on those hair cells. So again, it is mechanically gated. So when the gate is literally pulled open, potassium flows in, stimulates our action potential, and sends that to our brain. Okay, so to get to our brain, again, our hair cells move. They send those action potentials to our cochlear nerve. That cochlear nerve joins with our vestibulocochlear nerve, which is cranial nerve number 8. And the information from both ears is sent to both sides of the brain stem. This is where we're going to synapse onto another set of neurons that help to, one, tune the cochlea, so make sure you're hearing what you're supposed to be hearing, so just kind of get some feedback. But also because we need it for what's called binaural hearing. So if you might, have a app on your phone like for relaxation, and they tell you need to put your headphones in because you need to have information to be sent to both ears. What they're doing is they're trying to sync your brain by sending, let's say if you're trying to relax, so calm your brain down, they're sending one sound that's above where you need to be and one sound that's below, and hopefully between the two ears, you go to the frequency that you need. So that's what that's for. Okay, so binaural hearing is also knowing the direction from where your sound is coming from. So that's why you're comparing both sides to be like, which one's louder? And that way you're able to be like, oh, we're going from this side. It also helps with our startle response. So where you hear a sound and it draws your attention to that direction. And then eventually it goes to your primary auditory cortex so you can, one, detect that there's sound there. Then it's sent to your auditory your auditory association cortex so you can determine what you actually heard. So let's look at binaural hearing. So this again is comparing the sounds from both sides of the ears so that you can determine the sound location. So let's say you're listening to some great music. On the location from where it's coming from, the sound is a whole lot louder on one side, so you're going to have taller sound waves, you're going to activate that section of the basilar membrane more because you're going to cause more movement of that basilar membrane. So you're going to send more action potentials from this ear, while on this ear that is away from the sound, you're going to send less action potentials because the sound is softer. And so the brain can compare both sides, realize more action potentials is coming from the side of the sound location, and so that's the direction from where the sound is coming from. Okay, last section for at least hearing, and this is where I'm going to stop the video just because I don't want to get too long, is equilibrium. So this is knowing where our head is in space. So we have two different sections of our inner ear structures where we're actually determining head position. So this first one, the saccule and utricle, are determining just your normal head movement. So for example, the guy looking up towards, let's say, looking at the instructor or looking at a screen, his head is in one position. But if he looked down to write a note or look at his textbook or whatever, his head moves. The fluid in this area also is going to move. That's going to cause the hair cells, the hairs on the hair cells to move, and that's going to cause action potentials to be sent to your brain, as in, hey, the head is in a different position now. Soapbox moment, bending forward. Okay, bending backwards on your neck is bad. You don't want to go too far back because you can possibly damage the blood vessels in your neck from bending it backward. And that can actually lead to stroke. So please don't do that. That's why when you go to the hairdresser, they put that extra little bit of the extra towel in between your neck and the bowl of the sink to keep your neck propped up a little bit so you're not bending it too far back. Okay, off my soapbox. The other way that we're determining our head movement is with our semicircular ducts. That's what are these three. There are 3 different ducts in 3 different planes, since we live in 3 different dimensions. So one is upright, one is sideways, and one is kind of at an angle. So for example, the gymnast on the balance beam, one way to prevent the movement happening in the fluid in that area, what she's going to do is, as she's making her turn on the balance beam, she's going to keep her head steady for almost the entire turn, looking at a specific spot somewhere far off. She keeps her head on that one spot, and then once she gets to the point where she can't keep her head pointed at the same spot because her body is moving, then she whips her head really quickly so her brain doesn't have time to actually realize that there's been some head movement, and she goes right back to that same spot so the brain still gets the same position information, and that's why they're able to do that and not get dizzy. The same thing with like dancers on a stage. They'll look at a piece of scenery or something that's in far away, and as they're doing the turn and they're spinning and spinning, that's what they're doing. They're making sure that movement doesn't happen, and so the brain doesn't know that you spun, and so therefore you don't get dizzy. Another thing that your brain's also going to take into consideration is the vision of what's going on, as well as your hearing. Now, granted, I'm going to say this, and I'm just going to tell off on myself. I found this out in grad school. One time I was just kind of needing a break, and I got really bored. You actually can be spinning around even like as your head is still moving, turning around. So let's say if you're in like an office chair that you can spin around in, if you're able to block out all the sound, block out all the light, and keep your head nice and steady, your brain is not going to have the information that you moved because you're not moving the fluid in the semicircular ducts, and you're actually able to not be dizzy. But you have to not get in your light information, your sound information, or making sure your head doesn't move. So yeah, random. Yeah, sometimes you got to entertain yourself. Okay, so with our movement of the body, and this is the last one for this video. So with our different types of knowing where our body is in space, knowing our balance, we have our static equilibrium, that's the saccule and utricle, so where our head is just in one position, versus dynamic equilibrium, this is an actual movement of something. So either the movement or acceleration from a spot. So here we're just in one spot. Dynamic is where we're actually moving. So the first one, linear acceleration. So that's a change in velocity in a straight line, such as moving in an elevator. That would be the saccule and utricle. So you're going to have movement in your head region that tells your body, hey, we're moving. So movement of that fluid is going to be caused by that. And that's part of, it's a physics term called inertia. So something in motion tends to stay in motion. Something that rests, it tends to stay at rest. So once you get into that elevator, you know, your head is pretty stable, but then when you move, that causes the fluid, which should have moved as you move, but because it's at rest, it stays at rest. And so there's a little bit of change that happens there. It's like, oh, there's a fluid movement because now you're moving. And so, yeah, the brain knows that, oh, you're moving in one line. The other one is angular acceleration. So this is something like such as a rotation, like your car turning. So sometimes if you're driving and instead of keeping your head straight, you turn, you lean your body a little bit into the turn, and that way to keep yourself from getting dizzy as you're moving. And that is from your 3 semicircular ducts, which are determining your angle because they're in 3 different angles and able to determine where your head is positioned. Okay, so that is it for this video. The next one, the last and final one, at least for AP1, is this section on vision.